Okay, guys, so that is our differential amplifier. So first we will write the different expressions that we have learned so far in our previous lectures. The differential gain, start with the differential gain. So differential gain, the output we can take from either of these two collectors, or we can take output differentially between these two collectors. So for the gain we express if we take output from one single collector, VC1 by VID, that's differential gain from single landed output, and the gain is minus half JMRC. And if we take output from the other collector, collector 2, then the gain is positive. It is the same gain, but it is positive, and that will be plus half JMRC. And we can take the output differentially between these two collectors, and that will be then called VOD by VID. And that will be twice the gain of the single landed output gains. So that will be GMRC. So these ones we call the differential gain for single landed output. And this one is differential gain for this is differential output. Okay. And then we derive also in the last class, the input resistance for this differential amplifier, we call differential input resistance RID, which is 2R5. Also, the gains also we can express in terms of that we have seen in the last class from our T model of the differential pair, that VC1 by VID was minus alpha RC divided by 2RE, and VC2 by VID was plus alpha RC then divided by 2RE, and the last one is the differential gain for differential output, that will be just twice of this RC by RE. So these two are basically same, and that we have shown in the last class also. That is, you just use this relation that GM is alpha by RE, right? So if you use this GM alpha by RE, you get these relations. Guys, any questions so far? So now today's topic is differential half circuit. So what is differential half circuit? Okay, so to draw the differential half, first what we do, we set the VCC, the DC current and voltage to 0, right? That's the first step we do before we analyze the differential amplifier or any amplifier. So then the circuit will be left with, this will be connected to ground, right? And this part will become open circuit. Okay, so then our circuit will look like this. Let's go to the next page. Okay, so with the DC current and voltage sources removed from the circuit will look like this. Now VID, this is the differential input voltage here applied between these two the two bases of these two transistors. Now this will divide equally between these two transistors. So we'll have half of VID appeared here, and we'll have other half here, plus here minus here. So now here what the circuit would like to remove this part here. And this terminal is here. Now this part is half VID, positive on this side, and this is also half VID, but with minus sign here. Right? So with respect to this common point, voltage here is lowered by half VID, because we have minus here, plus here. So voltage at this terminal is lower, and the voltage at this terminal is higher with respect to this point by half VID. So if we take this as a reference point, so voltage here is lower by half VID, and voltage at this end is higher by half VID. So taking this as a reference, this we can indicate that this is here we have also we show like this, that this is voltage minus VID by 2, and voltage here is VID by 2 plus. So this side is plus VID by 2, and this side is minus VID by 2. And so the difference still remains the VID. Right? So that's the same. And that is our reference point. That's the common point, and voltage here is then 0 volt. Right? So with respect to this point, voltage here is plus half VID, and voltage here minus VID. So this must be 0. 0 point here, and this 0 point, this is for a small signal, right? Small signal voltage. So small signal voltage is 0 at this end. It's not the DC voltage and current. We have removed those, the DC bias voltages and current. So we can have DC, the bias voltage here. You can have 5, 10 volt DC voltage, but we are not considering the DC voltage. Those are already removed in our analysis. We are considering only this small signal voltage. So small signal voltage will be 0 at this point. We can have higher DC voltage, but that is not in our consideration now. The small signal voltage will be 0. So 0 means ground. So that will mean that we have a ground at this point for the small signal. So small signal voltage or current, they'll see that they'll feel that this is the ground. This point is at ground potential. Right? So we can show this like this. Similar to what we have here, the ground. Right? Ground means 0 volt, but this 0 volt, this is for small signal, right? Because we have DC voltage VCC, right? We have applied the bias voltage at the collectors, but we have set the collector voltage 0 for the sake of analysis. But in the real circuit, we do have the high DC bias voltage here. But That is the bias voltage, but small signal voltage is zero. Right? Signal voltage is zero. For the signal, it is ground. Similarly, for signal, this point is also at ground potential. Right? Though we can have DC voltage at this point. So if you show the like this, so you can also show it like this: the ground, same ground, right? These are the same points, right? You can show it in this fashion. Right? So it's the both of these emitter terminals, they are going basically to ground, right? Means they are at ground potential. So if that is the case, then you see that we can remove this line without changing anything in the circuit, because these 2 points still connected to ground. They are the same point though, but we are not showing it in the circuit, but they are the same ground. I mean, like these two collectors, they're going to the same ground, but they are not shown as being connected, but they are connected anyway. But we can show the circuit like this, and in this, when you show the circuit like this, it feels that these two are separate, independent circuits. Right? So, and each of these circuits, then we call them the each of these circuits we call them the differential half circuit. And we can use either of the circuit to analyze the different parameters for the amplifier. So let's use this one, the left part of the circuit, to analyze the amplifier. Let's see what do we get if you analyze the circuit using our the knowledge for the amplifier circuit and the small signal equivalent circuit. Okay, so there is our differential half circuit, and see this same circuit we can redraw. The same circuit we can redraw, and we can show this one like this. This is going to ground. And that is RC. And these are transistor Q1. So that looks more familiar, right? So these are load resistance RC in this case. And voltage here is half of VID. There is your input voltage plus on this side minus here, and the ground. And this our output here is VC1. And the different circuit parameters that we have, here the input resistance. We then amplify input resistance Ri, and that is our, from here we call it the output resistance. So this is the input and output resistance for this differential half circuit, not the differential amplifier. The differential amplifier input and output resistance will be twice of this, because there are two transistors, right? Now here we can draw the small signal equivalent circuit for this differential half circuit. and then it will look like this. Okay, we have R pi. Okay, so actually it goes here, and then we have this. It is connected to ground, emitter connected to ground. So R pi, the voltage here is VBE, and basically here VB is same as VID by 2. And okay, so the resistance that we see from here, that is our input resistance, and the resistance that we see from here, that is our output resistance. So now coming to the analysis of the circuit, so input resistance Ri is nothing but R pi. The output resistance R naught is small r naught, and then voltage VC1 is minus GMVBE. That's the total current. Total current multiplied by the total resistance. The here R naught and RC will be in parallel. So this current is supplying the parallel combination, so that we can write R naught in parallel with RC. Okay. Now that is our PBE is VID by 2. So then we can write that is GM VID by 2 R naught in parallel with RC. So we get the gain expression, which is PC1 by VID, which is minus half GM R naught in parallel with RC. Okay, so that is the gain expression. Now, what is the difference here in the gain expression? That if we compare with our gain expression with our previous gain expression, the VC1 by VID is minus GM RC. We have only RC here. We don't have the small R naught. That's the difference only. And why we didn't have this R naught? Because actually we didn't consider that small R naught, and probably in our first look it was not obvious to us that we have an output resistance here. But there is also an output resistance for this differential amplifier. So if you are looking into the terminal here, if you are looking into the terminal, so you will see an output resistance, and that is the R naught, right? And if you look into the terminal here, so also you see an output resistance R naught, right? So and there's the resistance between the collector and emitter, and that is the small R naught. So that is small R naught because now this part is for the small signal, let's say this part is ground and this part is also ground. So this R naught comes in parallel with the RC, you see. So there is an R naught that will come in parallel with RC. So that was not obvious in our first analysis. So now we have seen that this R naught is there. Okay, we have to move to the next step. So that is the gain, differential gain for single ended output if you take from collector 1. Then from our knowledge of the differential amplifier circuit, now we can easily deduce that the gain from the other collector VC2 will be, because that is positive and the gain is same as that we have for the collector 1, that the sign will be positive. So it will be half GM and R naught in parallel with RC, and the differential gain for differential output BOD by VIT will be twice this differential gain for single-ended output. So that will be just GM R naught in parallel with RC. So these will be the gain expressions. Now that also incorporates the output resistance on R naught into the gain expressions. And also we can find the input output resistance for the differential pair. The input resistance will be twice of this input resistance for the differential half circuit. So that is denoted by RIT, because we look between the two input terminals called the differential input resistance. RIT will be twice of RI, that the input resistance for the single transistor. And so this is 2R pi. And for output resistance, we will call it ROD, differential output resistance, looking between the two collector terminals, and that will be twice this output to R naught or to small R naught. Any question, guys? Is it all understood? Guys, are you there or you're left? You're all left.
No,
Yes,
sir.
sir.
No question.
So I think there is no question.
Okay. So now we slightly modify this circuit. If you include a resistance in the emitter, so what are the modifications that we'll get? So now that is the original differential amplifier without emitter resistance. Now you include, if you include a resistance RE, right? So how the differential half circuit it will modify, right? So then we'll have a resistance here, RE. Okay. So let's show it in a separate fresh page. So that will be our differential half circuit. That will be our differential half circuit of the differential amplifier with resistance in the emitter. So one thing the students always make mistakes is this, that the voltage at this point, at this end, is half of VID, and that is between the base point and the ground. Right? That includes also this emitter resistance RE. It's not between the base and emitter, rather between base and ground, that is half of VID. So when you draw the differential half circuit, so you have to put the correct voltage here, that is half of VID, or show like this. So there's the half VID, so that appears between the base terminal and the ground, including any resistance that you may have, right, in the emitter. So that is how the circuit will look like. And then to analyze the circuit, we can also show it like this, like before. So we can show it like this, that is, we are more familiar with. It's easy for our brain to process, right, the circuit, and then here we can show the input resistance Ri, and here we show the output resistance R0. Right? So we have already done the analysis of the circuit in our discussion on this single stage transistor amplifier, right, in the common emitter amplifier with emitter resistance. So we just use those right expressions that we have already learned to the. We don't need to go through the same steps again, and that is not very efficient, right? What are the different expressions that we derived for this common emitter amplifier with emitter resistance? First, we start with the input resistance Ri. It is first R pi, and then plus beta plus 1 Re. So that is applying the resistance reflection rule, that is the input resistance. The output resistance will be small r naught, and then that will be multiplied by this factor 1 plus Gm R pi in parallel with Re. So that will be the output resistance, both input and output resistance will get high value, and then voltage gain, the differential voltage gain in this case. Okay, so that will be the VC1 by VID. So the voltage gain for the differential amplifier is, voltage gain for the common emitter amplifier with resistance in the emitter. We have learned that the ratio of the two resistance on the resistance in the collector will have a minus sign, and the expression will be resistance in the collector divided by resistance in the emitter. So that will be the formula for the gain expression for the common emitter amplifier with emitter resistance. But in this case, the input is half of this, right? And we're taking twice of this. So actually it will be divided by 2, right? Since input is VID by 2, if you put VID by 2 here, then it's like this. But we're taking only VID, I mean, we're thinking in terms of the gain of the differential here. So it will be divided by 2. So that will be the gain expression. Now, resistance in the collector is just RC, and okay, RC, and the resistance in the emitter. Our emitter is the, we'll have a small RE here. If we look into the emitter, right, we have a small RE. So it will be 2 times small RE plus capital R. Right? So these are the different parameters, right, for this amplifier, common emitter amplifier with emitter resistance. Now from this we can deduce the other gain expressions. So that is the differential gain for if you are taking the output from the other collector. So VC2 by VID, and that will be just positive. This is negative, and that will just positive. The same, you have the same magnitude. So same expression, but with positive sign. And then differential gain with differential output, that is VOD by VID. So that will be twice of this gain. So it's just RC divided by RE plus RE. So you see that differential amplifier has a lot of similarities with the common emitter amplifier. The differential gain with differential output is same as what we have for the common emitter, but only difference common emitter we have a minus sign here. The is positive, but everything else input output is also same expression, but it will be twice of this, right? So the input resistance for the differential amplifier is denoted as RID. Called differential input resistance will be twice of this, twice of Ri, and that will be 2 R pi plus beta plus 1 small beta plus 1 Re, and the differential output resistance will be twice of this 2 R naught, and that we can write 2 small R naught times 1 plus Gm R pi in parallel with Re. Any question, guys?
No, sir.
Okay. Okay, so far we have considered the differential amplifier like this, and this is basically there is no load connected to this. This is without any load. If there is a load connected, we can connect the load either at the collector terminal of VC2, or we can connect the collector to VC1, or we can connect in between. I mean, between these two collectors, and we can show it like this. We have a load resistance that is connected between the two collector terminals. We can show like this VOD, the RL, right? So we are taking the output differentially, and load is connected between these two terminals. Then, if that is the case, then what will be the gain expression, right? Let's say what will be VC1 by VIT, right? How we determine that? So in this case, first what we have to see that voltage here, the differential output voltage is VOD, right? Plus on this side, minus on this side. Now we slightly change something here. Instead of RL showing as one single resistor, we can show it like this. Right. So we can show it like this. So we have here half of RL by 2, and we have other half here, RL by 2. Now see, total is still RL. Okay. Then what we'll have, and this voltage VOD will split into two halves. So we have VOD by 2 across this, and other VOD by 2 across this. So total is still VOD. Now, if you want to analyze the circuit, our usual procedure, we set this VCC to 0, the current to 0, right? So then these two are connected to ground, and this part becomes open circuit. So we can just remove this. Now what we see here, the okay, change this. Okay, so now if you take this as a reference point, the common point, like we did before, right, to draw the differential half circuit, if this is our common point. So then with respect to this point, the voltage here is lower by half of VOD, and voltage here is higher than this point by half of VOD, right? So VC2 is basically will be VOD by 2, and VC1 will be minus VOD by 2. Okay? With respect to this common point, voltage here is lower by half VOD, voltage here is higher by half VOD. then we can assign, like before, a 0 volt, right, at this common point. 0 volt means that this point is at ground potential for this signal voltage. We can have DC volt, but this point is at ground potential for this signal voltage. So we can show it like this, that it is at ground potential. Same way we shown that this point is at ground potential, right, for the small signal. So that means, okay, so let's remove this part. So it was plus VID by 2, and this was minus VID by 2. This was at ground, right? Both were at ground. And now this part is also connected to ground. Now see, RC here is also connected to ground. So it is obvious that now for a small signal, as long as small signal voltage and currents are concerned, this half of RL will be in parallel with this RC, and this half of RL will be in parallel to this RC, and then this we can redraw the circuit like this. So we just remove this part. And show it like this. We have RL by 2, and then also we have goes to ground and also RL by 2. And so that's the common point that was at 0 volt. Right? So now for what we can see, what is clear from this diagram, that the RL basically comes in parallel with RC, right? So if you want to draw the differential half circuit so that we can show like this, differential half circuit emitter going to ground, and then you have voltage here VID by 2. So there's our resistance Q1, and then we have here the resistances. We have RC, and that will be in parallel with RL by 2, and this is the voltage DC1. So that will be our differential half circuit. Any question, guys?
No, sir.
Okay. So now we can apply the different formulas to determine the voltage and the voltage gain, the input output ratio. So all those expressions remain same, just we will have a modification in the gain expression. So voltage gain, the for single ended output VID, which will be minus half GM, and then we have previously we have R naught in parallel with RC. Now we have another component here, that's the load resistance, that will be half of RA. So that will be our total gain expression for the single ended output from collector 1. If we are taking from the second collector, collector 2, then it will be plus, right? Just plus and the same gain expression, not RC in parallel with half of RL. And if you are taking output differentially, then VOD by VID, that will be twice of this gain, and that we can write as GM R naught in parallel RC in parallel half of RL. Okay. And the input output resistances remain same because that is you're looking from here, that is you see R5, and if you're looking from down here, the output resistance will be small R naught. So they remain same. Only we get the modification in the gain expression. Any question, guys?
Sir,
Yes.
about the grounding, sir. Sir, are they
What?
grounded with some kind of, sir, the
What?
signal grounding, sir?
What grounding?
Sir, the small signal grounding.
Okay.
Sir, are they grounded through any capacitors or something like that?
Grounded to what? Didn't get your question.
Sir, are they grounded through any capacitors?
No, no, no. There is no capacity here. Their ground potential 0 volt. That means the same as the ground, right? There can be high DC voltage, but the small signal voltage is 0 at that point. So that's basically at ground potential, and we can show it like there is a ground at that point. It's already connected to ground, right? So it is like this. You have a point in the circuit that's not directly connected to ground, but probably there is a voltage source. So at this point, you have a DC voltage, right? You have a DC voltage. DC voltage is constant, but AC voltage is 0 because AC means there has to be some fluctuation like this, right? But there is no fluctuation. You have a constant voltage. So that is DC voltage. And you have some DC voltage here, some amount of it can be 5 volt, can be 10 volt, it can be low, it can be high. But as long as small signal is constant, the small signal voltage, there is no fluctuation, is constant. So that is 0. And for this source, ideal source has 0 resistance, right?
Yes, sir.
Yeah, ideal source 0 resistance. So AC voltage, this point is basically actually the same as the ground, right? Because that is shorted because no AC voltage, right? So for AC, this is like connected to ground, right? And this is how it you can think of it, right?
Yes, sir.
Okay. So now you can also have resistance in the emitter for this case, as we have discussed before, right? You can also have resistance. Then just you have the modification in the gain expressions. Therefore, with resistance, that will be VC1 by VID. So that will be resistance in the collector divided by with a minus sign for VC1. Resistance in the collector will be, okay, I get rid of this one, it's coming in the way. So resistance in the collector in this case will have RC in parallel with half of RL. So that will be resistance in the collector. Divided by resistance in the emitter, that will be, okay, we will have half. And then small RD plus capital R. So that will be gain expression for one single, the collector terminal, and if you are taking differentially VOD by VID, that will be repress RC in parallel with RL by 2, and then we have RE plus small r. And the input and the output resistance is same as that we have shown in our previous diagram for the differential amplifier with resistance in the emitter. Any question, guys? So that will be all for today's class. Next class we will discuss about the common mode half circuit. So common mode means when you apply the same voltage to both the input terminals, you are applying common voltage, how the circuit works and what are the gain expressions for that.